Imagine you're watching the night sky over the United States. You see nothing unusual, no aircraft, no explosions, no warning. And yet, somewhere thousands of miles away, a missile has just launched. Its engines ignite. A massive heat signature appears. And almost immediately, a satellite sees it. Not a radar station, not a fighter jet. A satellite hundreds of kilometers above Earth. That satellite sends the information into a network. Other sensors begin tracking the object. Computers calculate where it's going. And suddenly, American commanders have something they didn't have a few seconds earlier: time. But here's where the story gets interesting. What if America didn't just want satellites to watch the missile? What if it wanted the ability to stop it from space? That is the basic idea behind America's emerging space-based missile defense ambitions. And it raises a much bigger question. Why would the United States put part of its missile defense system in orbit when it already has some of the most advanced missile defenses on Earth? The answer isn't simply about having better weapons, it's about one thing: seeing the attack earlier. Because in missile warfare, the difference between seeing a missile early and seeing it too late could determine everything that happens next. For decades, America's missile defense architecture has relied heavily on systems on Earth: radars, ships, interceptors, command centers, aircraft, all connected into increasingly sophisticated networks. But there's one problem they can never completely escape. They're on Earth, and Earth is curved. A radar sitting on the ground can't see forever. The horizon gets in the way, terrain can interfere, low-flying weapons can exploit the atmosphere, and an attacker gets to choose where the attack begins. Now move the sensor hundreds of kilometers above the planet. The geometry changes completely. A satellite can watch enormous areas. It can detect the infrared signature of a missile launch. And with multiple satellites working together, the United States can potentially build a much more persistent picture of what is happening. That's the thinking behind the emerging American space-based missile defense architecture. The Space Development Agency's tracking layer is designed to provide global missile warning, tracking, and targeting capabilities, including against advanced threats such as hypersonic weapons. And this isn't purely theoretical. The United States is already building out additional missile warning and tracking satellites. But detecting a missile is only the beginning, because knowing where the missile is doesn't mean you can stop it. And that's where the most controversial part of this strategy begins. A missile's flight isn't one single event. It happens in stages. And one of those stages could offer something incredibly valuable to a defender: an opportunity. Immediately after launch, a ballistic missile's engines produce enormous amounts of heat. The missile is accelerating, it's climbing, and its infrared signature can be extremely powerful. This is called the boost phase, and theoretically, this is one of the most attractive moments to intercept a missile. Why? Because the missile hasn't yet traveled most of its journey. If you could stop it here, you might never have to deal with it later. That's why America's current missile defense plans have included the development of proliferated space-based interceptors capable of boost-phase interception. But there's a problem, a huge one. The interceptor has to be in the right place at exactly the right time. And space isn't stationary. Everything is moving. The satellite is moving, the missile is moving, the Earth is rotating, the target may be changing course, and the window to act can be extremely short. Which means the real weapon isn't simply the interceptor, it's the network behind it. Imagine you're trying to hit a speeding car, but you don't know exactly where the car is. You only receive information from cameras scattered across an entire country. One camera detects it, another tracks it. A computer predicts where it will be, a third system sends the information to an interceptor, and the interceptor has to reach the correct point at the correct moment. Now, make the car move thousands of times faster, and put the entire system hundreds of kilometers above Earth. That's the challenge. A space-based missile defense system would need to answer several questions almost instantly. Where was the missile launched? Where is it now? Where will it be next? Is it actually a missile? Is it a decoy? Is it maneuvering? And most importantly, can the interceptor reach it in time? That's why America's concept is much bigger than put missiles in space. It's closer to build a nervous system around the planet. Satellites detect, networks communicate, computers process, command systems decide, interceptors act, and the faster those pieces work together, the more useful the entire system becomes. But then the target changes. Because not every missile behaves like a traditional ballistic missile. Imagine knowing exactly where a car is going. You calculate its route, you predict where it will be 10 seconds from now. Then suddenly, it turns. You recalculate, it turns again. Now imagine that vehicle moving at hypersonic speed. That's part of the challenge created by advanced hypersonic weapons. Traditional ballistic missile trajectories can be comparatively predictable, but maneuvering hypersonic weapons can complicate that calculation. They can change direction, they can operate at different altitudes, and they can reduce the time available for a defender to react. So missile defense becomes a race. The sensor races to see the weapon, the network races to report it, the computer races to predict it, and the interceptor races to reach it. That is why space-based tracking is so important. But now imagine something even worse. The attacker doesn't launch one missile. They launch dozens. Imagine America has built an incredibly sophisticated missile defense network. Satellites are watching, radars are scanning, ships are ready, interceptors are waiting. Now an adversary launches a massive salvo. Suddenly, the question changes. It isn't, can America stop a missile? It's, can America stop enough missiles at the same time? And that's one of the hardest problems in missile defense. Because an attacker doesn't necessarily need to defeat the entire system. They only need to get enough weapons through it. They could use large numbers of missiles. They could use decoys. They could use electronic warfare. They could attempt to overwhelm sensors. They could attack the satellites themselves, or they could develop weapons specifically designed to exploit weaknesses in the defense network, and that's why the word proliferated matters. Instead of depending on a small number of extremely expensive and vulnerable satellites, build a much larger network. If one satellite fails, others remain. If one part of the network is attacked, the rest can continue operating. The goal isn't to build one perfect shield, it's to build a system that is difficult to break. But that creates another problem. Because the larger the network becomes, the bigger the strategic competition becomes. This is where the story becomes much bigger than a few satellites. You may have heard the name Golden Dome. It can sound like America is trying to build one giant shield over the country, but the concept is much more complicated. Think of it as multiple defensive layers: space-based sensors, ground-based radar, command and control systems, sea-based systems, existing interceptors, new interceptors, and potentially space-based interceptors. The first layer could detect the launch. Another could track the missile. Another could attempt an interception. And if that fails, another defensive layer could get another opportunity. The goal isn't necessarily to make America completely untouchable. It's to create multiple chances to stop the attack. And that distinction is incredibly important, because no missile defense system can guarantee that every incoming weapon will be destroyed, but it can force an attacker to solve a much harder problem. And that leads to the biggest question of all. What happens when the shield gets stronger? Imagine America builds exactly what it wants: a huge network of satellites, persistent tracking, faster detection, better interceptors, multiple defensive layers. Now imagine Russia or China looking at that system. They don't necessarily have to copy it. They can try to defeat it. More missiles, more maneuverability, decoys, electronic warfare, new trajectories, counter-space weapons, different types of warheads. And suddenly, the competition isn't simply about building a better missile, it's about building a missile that can survive the entire defense network. This creates a familiar cycle in military history. The sword gets better, the shield gets better, the sword changes, the shield changes again. But there's something different this time. The shield itself is moving into space. And once satellites become critical to America's missile defense, those satellites become strategically important targets. That means a system designed to protect America could also become part of a new competition over who controls the most important military infrastructure in orbit. And that is why this isn't simply a missile defense story. It's a space strategy story. Can America actually build it? Now we need to separate the ambition from reality. Putting a satellite into orbit is difficult. Putting a sophisticated interceptor into orbit is harder. Making that interceptor detect the correct target is harder still. And making it intercept a rapidly moving missile during a narrow window of opportunity is an extraordinary engineering challenge. Then there's the cost. The FY 2026 defense budget request included approximately $25 billion associated with Golden Dome and related missile defense efforts. That's an enormous investment. And even that doesn't guarantee an impenetrable shield, because the attacker gets a vote. They can adapt. They can increase the number of weapons. They can develop new trajectories. They can use countermeasures. They can target the satellites. They can look for the weakest point in the network. So the realistic objective isn't stop every missile, it's make a successful missile attack much harder. And that distinction may be the most important part of this entire story. The real reason America is looking up. So, why does America want missiles in space? It's not simply because America wants bigger weapons, it's because the missile threat is changing. Weapons are becoming faster, some are becoming more maneuverable, some are becoming harder to track, and the time available to make a decision is shrinking. America's answer is to move part of its defensive architecture higher above the Earth. Satellites can detect launches, tracking systems can follow them, networks can move information, computers can process it, ground and sea-based systems can respond, and potentially, space-based interceptors could create another opportunity to stop a missile before it reaches its target. But this isn't a magical shield. It will be expensive. It will be technically difficult. And America's competitors will almost certainly look for ways around it. So the real story isn't America wants missiles in space. The real story is this. America wants space to become the first place a missile is detected, and potentially the first place it is stopped. Because in the next generation of warfare, the most important weapon may not be the one that hits hardest. It may be the system that sees the attack first. And if America can build that system, the battlefield may begin hundreds of kilometers above Earth. If you want to understand the military technology changing the balance of power, from the F-35 and B-21 to Golden Dome and space-based missile defense, subscribe to the channel.